Hello, everyone. Today we're going to continue talking about homeostasis. We will look at some examples of homeostasis diagrams, and we will talk about homeostatic mechanisms and some of the features that are found in all sorts of homeostatic mechanisms. And we will also compare positive and negative feedback loops. So, you might recall from last Wednesday, homeostasis is the tendency of the body to maintain a stable, balanced internal environment. In other words, a sense of sameness. Homeostasis is what keeps your body temperature at a normal 98.6 degrees Fahrenheit or 37 degrees Celsius. It maintains your blood pressure. It maintains your heart rate, the amount of glucose in your blood, the amount of water and salt in your blood. Homeostasis is so important. If your body stops maintaining homeostasis, you are dead. So first we're going to talk about negative feedback loops and how they help maintain homeostasis. Every feedback loop contains three things. First, we have receptors. These are body parts that detect certain environmental changes within the body, such as temperature, and that information is relayed to the brain typically. But these are body parts that detect some type of change, some type of stimulus. The set point, this is the normal range that an environmental parameter is controlled. So, for example, human normal body temperatures is about 98.6, and that's where homeostasis is going to keep us. If you get any lower than that, you're hypothermic, too cold, or any higher than that, you are hyperthermic, or too hot. If you get too low or too high, it ends in death. So, any change away from the set point is detected by the receptors. Effectors are other body parts, usually muscles or glands, that respond to the change from the set point. Glands might initiate sweating to cool the body down back to its set point if we're talking about temperature. So here is an example of a negative feedback loop. Usually these diagrams look like a figure eight, and we're going to have some practice when we are in class looking at these diagrams. But we start at the middle. This is your set point, our normal body temperature. If our temperature gets too high, let's say we're working out or it's just hot outside, that is a stimulus that is going to activate our receptors in our brain. So our receptors are going to say, hey, we're getting a little warm here. We need to cool the body down because our body temperature is too high. So then that receptor is then going to relay a message to effectors, and these are muscles or glands. So in our blood vessels, we have some muscles, and those muscles dilate, meaning they get wider. And when they get wider, more blood flow is sent to the surface of the skin. That's why some people turn red when they're really hot. It's just because there's way more blood flowing to the skin. And then our glands, sweat glands in our skin become activated to start producing sweat to help cool our body down. As the body does this, our temperature drops. This is why this is called negative feedback, because the temperature started going up, but then the response to that initial stimulus was that we bring the temperature back down. If our body temperature gets too cold, the receptor, the brain, will become activated again. And instead, it will do the opposite. It'll tell the muscles in your blood vessels to constrict, meaning they restrict blood flow and redirect blood to your vital organs. That's why your ears and your fingertips get cold really fast, and these are the first body parts to get frostbites because there's very little blood flowing to them. And then it will send a signal to your muscles to start to shiver. And as you shiver, and as your blood is kept deep within your body temperature will start to rise and you come back to homeostasis. This is also negative feedback because our initial stimulus, the decrease in temperature, was reversed by our body parts. So if the initial stimulus, is reversed, it's negative feedback. The one thing that I want to make very clear is that negative does not mean bad. For example, let's say you wrote a paper, an English essay, and your teacher gave you a lot of feedback, and you might feel bad about it because there's a red marker and red ink all over your paper, but that feedback is meant to help you fix your mistakes, which is a good thing. By giving you some negative feedback on your essay, you know not to make the same mistakes. So you stop making those mistakes and instead you do the opposite. You do fix those mistakes and improve your writing. Negative feedback just means that the initial stimulus is reversed. So you make a mistake on your paper, you get some feedback, and you fix it. You stop making those mistakes. When we're talking about the human body, any change away from that set point is a stimulus. And we want to reverse that stimulus so that way we can return the body back to that set point. And this is good for maintaining homeostasis. So, negative feedback is really important for our bodies. It is by no means a bad thing. In addition to negative feedback loops, we also have a few positive feedback loops that occur in our body, and these are very rare, and I'll explain why in a minute. Unlike negative feedback loops that reverse a stimulus, positive feedback loops amplify the stimulus or they make them stronger. And one example of this is childbirth. If you have ever seen a woman who is in labor, you might know that contractions get stronger and stronger as you get closer to the birth. So, how positive feedback loops happen is that we have an initial stimulus. In this childbirth example, that initial stimulus is that the baby gets big enough so that the head presses on the cervix. Once that happens, a signal is sent to the brain, and the brain releases a hormone called oxytocin. And that oxytocin then travels through the blood to the uterus, which causes the uterus to contract. As the uterus contracts, it pushes the baby's head down even more on the cervix. And so it pushes against the cervix, and then the cycle starts over and over again. And the contractions get stronger and stronger and stronger until the baby is born. Once the baby is born, there's no more baby's head pushing on the cervix, and so this feedback loop stops. Another example is blood clotting. When you get a cut, platelets in your blood become activated and become really sticky, and they'll release chemicals to recruit other nearby platelets to activate and become sticky to help form that clot. and more platelets become active until the bleeding is stopped. So that initial stimulus of the platelets becoming activated increases and increases and increases until there's no more bleeding. So this is a positive feedback. We have an increase over and over. The response increases the stimulus until the stimulus is gone. These are very rare in our bodies. Childbirth and platelets and also lactation, milk production in women are just a few of the positive feedback loops. Positive feedback loops are they do not return the body to a set point the way negative feedback loops can. Instead, they bring your body further and further away from a set point. So, for example, let's say temperature was controlled by a positive feedback loop. If you got cold, a positive feedback loop would make you colder and colder and colder. And if you get too cold, you die of hypothermia. So, positive feedback loops are not always good in the human body. In these circumstances, yes, a woman can't stay pregnant forever. You need to have blood clotting to keep you from bleeding out. But for the most part, negative feedback loops are what is going to help us maintain homeostasis.